Thank you all for coming. My name is Doug Hawkins. I work on the Java virtual machine at a company called Azul Systems, as he said. We are known for, historically, our Java appliance, which was a custom-built machine to just run Java fast with lots of cores. We've since switched to targeting x86 directly, but we still shoot for big Java applications. We support presently a terabyte a heap with very little pause. Soon it will be 2 terabytes a heap. I actually don't work on the GC, so oddly enough, despite the fact that we're known for GC, I'm not going to really talk about it. I'm going to talk about the just-in-time compiler. What I actually work on is our Ready Now technology for low latency Java applications. Think high-frequency traders. And getting rid of the tiny pauses that are left over after we've solved the GC pauses. But I understand that most of you don't run Zing. That's our high-end one. But we also have an OpenJDK offering, Zulu. And OpenJDK is pretty much like HotSpot. So I'm just going to stick to HotSpot since that's what most of you are probably using. And frankly, the techniques are pretty much the same regardless of which VM we're talking about. There's slight differences, but they're not really important to the talk overall. At a high level, the goal for today is to just understand the HotSpot lifecycle. HotSpot, as you know, has an interpreter, unlike, say, C#. And we start off running our Java bytecode in the interpreter. The classic VMs, or as I like to call them, the antiquated VMs, just had an interpreter, and Java 1.1.1 ran dreadfully slow. Think Ruby or Python. I'm sorry, they just have an interpreter. We also, in HotSpot, now profile. So we follow your program around, seeing what it's doing, and seeing if we can use those assumptions. It's not all that different than, say, branch prediction in hardware. We actually do branch prediction just in the VM. All that's fed into the just-in-time compiler. And the just-in-time compiler, because it's in a managed environment, can do things that your average C or C++ compiler cannot. Yes? Yes, so in the newer VM with tiered compilation, you have profiling, some in the interpreter, and then also some more in C1, depending on the mode you are in, whether it's only tier 4 of C1 actually does profiling. So, yes, we will get there. The details will follow. And we may deoptimize, because we can actually speculate that something will be true, and if it turns out not to be true, we can correct it. A C or C++ compiler cannot do that. And that turns out to be really important to making a dynamic language run well. And yes, I count Java as a dynamic language. But more specifically, my goal is actually to get you to understand this piece of code, or at least what the compiler is going to do to it. It's array list for each. It's added in Java 8, so hey, it's new and cool. It takes a function object. We loop over the size of the array and pass each element to the array, or to the function. That's it. Like, really? We're going to spend an hour talking about 5 lines of code. Yes, yes we are. There is that much here, I assure you. Now, the actual implementation turns out to be this. There's some stuff here for the mod count, which is to do concurrent modification exceptions. But the more interesting part is these local variables at the top. They have done that for a reason. It's just going to take us a while to get there and understand why. We're going to have to understand a bunch of things. We're going to have to understand dynamic compilation, when it kicks in, what kind of static optimizations the compiler does, what kind of speculative optimizations a JVM does, something about interprocedural analysis, and if we're going to do speculative optimizations, we're also going to have a way to fix our speculations, and that's the deoptimization. So we're going to see all of that in those 5 lines. And my real goal in this is just to get you to understand how HotSpot thinks about your code. The compiler's really honestly not that smart. And there are ways to trip it up. And I want you to understand what it does, what kind of analyses it does, so you can work with it rather than against it. Working against it is likely not a winning strategy. A compiler will go and second guess what you're doing. It will say, you did that. That's kind of a weird way to do this. I'm going to do it that way instead. It will do this. I'm going to stay within the area that you actually have some influence and can help the compiler. All right. First, when does HotSpot JIT? This does actually change. It's changed very significantly in Java 8. It was an option available in Java 7. But we'll take a simple piece of code. Here I have a random array of ints of size 1000. I'm going to do a crappy way of benchmarking it by having a for loop from I to 0 to 500. I'm going to take the nanotime inside, and I'm going to sum up the values. This benchmark could easily go south, but it's enough to illustrate the point. This is the program we're running. And there. It starts off in this 55,000-ish range. That's the interpreter. It quickly sort of improves to around 20,000 nanoseconds. Gets a little better, and then finally it drops down to usually around 2,000 or 3,000 nanoseconds. There are some GC pauses in here, not from the sum, obviously, but from the I/O, which is building strings. That's why it's not a very good way to do a benchmark. There are code references down in the corner. I will post everything online as soon as Meetup's file upload is working again. It was not working today. And you can go look at each of these and run them yourself. They're also all annotated with the VM flags you might want to run them with. Now, if we just go and plot this, you get this. There's this huge GC spike. It kind of dominates the graph. If I put it on the log scale, then you can actually start to see the JIT behavior. There are these values at the very beginning that are in the interpreter. The first just-in-time compiler kicks in. Numbers get a little bit better. And then the other just-in-time compiler kicks in, and they drop even further. They could theoretically, in this case, actually drop all the way to 0 because I'm actually not using the result of sum. And the compiler can do dead code elimination. Didn't happen in this benchmark. There are plenty of benchmarks where it does happen. You can easily lie to yourself. You can also see that if you were trying to benchmark this and you benchmark the wrong phase, you would get completely skewed numbers. If you benchmark at the very beginning for a short period of time, you're getting only the interpreter. Your values will be disproportionately high. If you care about warm-up, then maybe you want to do that, but that's usually not what people want. You really want it to reach a steady state to get to the second JIT. If it hasn't done that, it kind of doesn't matter because, well, that method's ice cold, to be honest. Now, HotSpot and pretty much most just-in-time compilers at this point are method just-in-time compilers. They compile whole methods. The alternative is what's called a trace JIT, where you kind of draw a line through the hot path, like this if only goes this way. I'm only going to evaluate that part, and it can actually carry across methods. Those do exist. That's what Android uses for Dalvik. That's what a lot of the JavaScript engines used to use, but they've increasingly gone to being method JITs. I'm not going to explain why, but basically, it's pretty simple to make a method JIT work. You just say, if a method's been called a lot, it's probably hot. That's it. You have a counter. How many times have been called? Let's compile that. there is more to HotSpot than that. If I ran that program from before with this flag -xx : print compilation, which you can use on a production VM, you'll see this sort of output somewhere around the 67th iteration sum. It will do a just-in-time compilation of sum. And then it does another one at the 75th. Now, the way you read this is the left column is the time since the VM started in milliseconds. The next column over is a compilation ID. They're just assigned sequentially. The actual sequential assignment varies a little bit if you were using Java 6, which is end of life and you should not be using, but it may not look exactly like this. And it definitely won't look like this unless you're using Java 8, which has this extra tier column. Now, we know there are 2 tiers of JITs. So why does it say 3? We'll get to that. Then we have the method name. One of them has this number after it and a % before it. And then a little bit later, we see one at tier 4. As you can imagine, that's the step after 3. And these roughly correspond to where the numbers get better. I'm going to actually put them on the graph. The tier 3 compilations happen about here, which is very close to where it got better. The tier 4 compilations happen here, and there's a bit of jitter, but then it starts to settle down and get better still. So it's pretty common to have 2 JITs. So she asked why we have 2 JITs. In part, it's out of a historical accident. There were 2 different HotSpot VMs up until Java 7. There was the client VM and the server VM. And they had 2 different JITs designed for 2 different goals. The client VM was designed for swing applications, which I know is what everyone here is writing. Yeah. But it's designed for warm-up because no one likes staring at the Eclipse splash screen. We want our applications to launch quickly. If we're just launching an application, we don't want to sit there and wait. But after that, let's be honest, we're ploddingly slow humans. We don't barely notice a 100 millisecond delay. It's really like a UI guideline. You need to respond in 1/10 of a second. So we don't really need to run all that fast. After all, most of the time the application is just sitting there like, are you going to move the mouse? Come on, move it. Click. Come on, click. I'm bored. Now, the server VM was designed for exactly the opposite thing. We're not restarting this program very often. Your ops department doesn't really care so much that it takes WebLogic 3 days to start, right? They just start it 3 days before it needs to launch, or, okay, 15 minutes. And that's not a big deal, because it's just going to be up all day, or days. But it could be serving many ploddingly slow humans, in which case we'd like it to go fast, so that when this human's not doing anything, we can do something for that other human. Or worse, it's serving a whole bunch of other machines. And then speed is of the essence. So one was designed to launch quickly, compile quickly, but run slowly. The other one was designed to start slowly, compile slowly, but run fast. And then, of course, someone said, huh, they do 2 different things that sound complementary. Maybe we could put them together. And that's what tiered compilation is. It does exist in other forms. If you look at any JavaScript engine, all of them have some form of tiered compilation. You usually have a relatively unsophisticated compiler first. This is true in V8, it's true in JavaScript Core, it's true in whatever Firefox is calling their monkey now. And then you have an optimizing tier, or maybe two. JavaScript core actually now has 4 tiers: an interpreter, a not so smart compiler, a moderately smart compiler, and a smart compiler. Okay, let's try to be a little more specific about when we JIT. Now, I could show you what the thresholds are. You could actually do this yourself. You just go to type Java -XX : plus print flags final, and it will tell you all of the values the VM has decided to use on the piece of hardware you're running it on. Now, it may choose different values on a different piece of hardware, but you can do this. If you then grep for threshold, you'll find these. This doesn't tell you a whole heck of a lot. There are some new ones for tiered compilation in Java 8, and there are some other ones that don't have tier on them for Java 7 and earlier. What those thresholds correspond to are counters. There is an invocation counter for the method, as I already said, but there is another one that's a little more specific to HotSpot. It's less common in other JITs. There is a back edge counter, or more simply put, a loop counter. Every time you go around a loop, it adds 1. There is 1 counter for the whole method, no matter how many loops it has. We don't have room for all those counters. We just have 1 for all the loops. And we increment it. And, well, just by law of averages, the loop that we go around a lot will probably be the one where the counter goes over its threshold in. Right? This loop is used 9 times out of 10. That one's used 1 time out of 10. Well, most of the time the counter will trip in the right loop. If it doesn't, we'll try again later. So we can use that to compile hot methods and hot loops. There's still another problem. What if I have a method that's used a little bit? Like, say, array list for each. I call it sometimes, but it takes a function object, and our array list contains a couple thousand items. So we have a moderately hot method with a moderately hot loop. Shouldn't we compile that? We still have instructions that we're using just the same number of times. And the answer is yes. There is a compile threshold that is actually when the invocation and back edge counter together exceed some number. So there's an invocation threshold. If you're over that, you compile the method. There's a back edge threshold. If you're over that, you compile the loop. And then there's the compile threshold, which is a combination of the two, where, again, you compile the method. So HotSpot is not just a method JIT, it is also a loop JIT. As far as I know, this is not true of most of the JavaScript engines. Now, HotSpot calls this loop JITting on-stack replacement. The reason it calls it that is because you have to imagine what the VM is doing. It has a bunch of interpreter frames on the stack. Mid-running this method on the top of the stack, we decide, oh, you have a hot loop. Maybe I should JIT you. But you're in the middle of running. So now we have to make a new compilation. The layout of the interpreter and the compiled frame are not the same. So you have to copy all the data from the interpreter frame into your new compiled frame, and then throw the interpreter frame away and put the compiled frame on the top of the stack to do this. So you're replacing a stack frame. That's why it's called on-stack replacement. And you can do it in reverse as well. That is actually important to being able to do deoptimization. And to me, that's another form of on-stack replacement. HotSpot only calls loop compilations on-stack replacement. And now the tiers. We saw tiers 3 and tier 4. What happens to tier 1 and 2? Yeah, we don't use those most of the time. Rather than just going from interpreter to C1 to C2, that is, interpreter to the client compiler to the server compiler, the scheme is slightly more complicated. There are 5 tiers. Tier 0 is the interpreter. Tier 4 is C2. That's usually the end goal. That's the server compiler, the one that's fast. C1 is our intermediate waypoint. And tiers 1, 2, and 3 are all C1. Why? It all does the same optimizations every time. Well, that's probably mostly true. Well, the reason is it does extra levels of data gathering. To get from the interpreter to, say, tier 3, we pass a threshold. In tier 3, we also have to have counters so that we know when we pass the threshold to go to tier 4. But C2 is what is called a speculative profile-guided optimizing compiler. It needs data about what the program is doing, down to an individual instruction level sometimes. Well, branches, call sites, but quite a few places. That's expensive. That adds 30% to the execution overhead of C1. It's non-trivial. Now, when the application is starting up, C2 could be very busy. This is when almost all JIT activity occurs. Right? Like JIT happens at the beginning, and then it pretty much stops if you have a well-behaved system. And so at the beginning, C2 is busy, and it may not be able to get to us. And so if it can't get to our compilation anytime soon because its queue is really long, is it worth paying the 30% execution overhead right away? No. So in that case, when we go from the interpreter to C1, we'll say, well, it'd be nice if we could go and get the data for C2, but C2 is busy. So let's just go to tier 2 instead, which has to have counters so that we know when to go from 2 to 3 to then get the data to then give to C2, tier 4. But it's much less overhead than having counters and instruction level profiling. Okay, what about tier 1? It is for trivial methods. There are certain things that C1's perfectly good at. C2 has all sorts of crazy fancy loop optimizations that we're going to get to. But say something like the object constructor. It's a single byte. It is a return. This is not a terribly hard thing to compile, no matter how smart your compiler is. So rather than burning our C2 budget on things like that, what will happen is you'll start off in 0. You'll go to C1 in tier 3 or tier 2, and it will say, that wasn't very hard. And I don't need any more information to do this. So I'm just going to instantaneously recompile in tier 1, which is C1 without any overhead. No counters, no instruction level profiling. The hope here is that for trivial methods, C1 tier 1 is just as good as C2 tier 4. So your end goals are 4 and 1. It probably sounds a little strange, but that is the case. And if you looked really hard at the print compilation output, you'd find a line somewhere in there that says, this compile from before got made not entrant. That's not saying that it was compiled again. That's actually saying I'm done with that compilation. I'm going to lock out anyone using that compile again. At the very beginning of every compilation, there's a check that says, should I actually be used? If no, okay, kick the caller out. The reason this exists is so that we can do a lock-free cache invalidation. The caller will actually cache the address of the compiled piece of code after it's gone through finding the callee method and then finding out that it's already been compiled. And now we would like to get the callers to move to a new, better version. But we don't want to have to stop the world, take a big lock to do that. So we atomically block access at a hardware level with a single update at the beginning of this, so that the new call will be forced to go back to the call dispatcher, and then the call dispatcher will reroute through the method and find that there is a new, better compile. So the transition doesn't actually incur a stop the world pause. There are things that incur stop the world pauses. We will get to those. Now, the basic mechanisms of this, they haven't changed very much, to be honest, other than this introduction of tiered in Java 8. But tiered is still a work in progress. It was on by default ever so briefly in Java 7 until Oracle realized it made one of their own programs slower and turned it back off again. Now, they've turned it on again by default in Java 8. But if you actually look at what the thresholds are from an early Java 8 release to a later Java 8 release, it's changed. They're still tuning this. For the most part, unless you had a really gnarly warm-up problem, you wouldn't care. The only thing you really need to know is that HotSpot finds hotspots. That's where the name comes from, both methods and loops. Okay, that's a cursory explanation of how the JIT actually kicks in. So what does it do? And I only really care about the server compiler. That's actually where most of the effort towards optimizing goes, because that's our end goal. There is some work going into C1 because it's our end goal for things that are classified as trivial methods. And C2 is, as I said, a profile-guided optimizing compiler that speculates. And we're going to have to see what all those things are. So returning to for each. The first thing that compounds the work for Java's compiler is we have to put in safety checks. I'm actually going to switch from using array list for each to a sort of theoretical array stream for each, because then I don't have to deal with this size here. I have to use this element data length, which is actually easier for the compiler. You think it looks harder, it's actually easier. Now we put in all the safety checks. First, we have this element data length. Well, before we can do that, we first have to check, is this null? Okay, that's obviously not the case. But if it were some other variable than this, we'd have to check it. All right? Then we have to check, is this element data, is it null? Then we can check the length. Theoretically, we have to do the same thing inside before we can actually access an element of the array. We have to check this. We have to check the element data. And we have to do our bounds checking. We have to say, is I less than 0? Then we have to throw an array index out of bounds exception. Is I greater than or equal to this element data length? We'd also have to throw an exception. And we have to check if our function object, our action, is null as well. Yeah. It's the compiler's job to get rid of all this. And it's your job not to screw it up. All right, this equals null. If this were null, we already threw a null pointer exception before we called this method. That can't happen. Those two checks are gone. Excellent. Now we're going to look at the bounds check. I less than 0. The compiler will go, I starts at 0. I is incremented by a positive 1. Does that mean that I has to be between 0 and int max? No, because we could wrap. Okay? In C++, that's okay. In C++, there are no semantics as to whether there's overflow or not. It's allowed to assume that doesn't happen. Instead, in Java, what we have to do is say, well, this element data length, that's an array. And arrays can only have positive lengths between 0 and int max. So we can constrain I to a value between 0 and int max. I guess those should have been greater than or equal to, less than or equal to. So I cannot be less than 0. This is actually done through a type system inside of the compiler. The cruel joke about statically compiled languages is we don't care about your types. The Java bytecode actually doesn't store a lot of the type information. We deduce it by looking at the right-hand side and figuring it out. Does that sound like any other languages you know? Yes. So we're just being mean. We're making you type it. We don't even use it. We're going to rediscover our own more precise type information anyway. Now, the upper bound check. The first step is to actually do what's called canonicalization. So we take that I greater than or equal to the element data length, and we turn it into not I less than the element data length. How is this better? It's better because now the compiler can see, oh, I already checked that up here. And so it has this common sub-expression where it can say, well, if I'm inside the loop, I less than the element data length must be true. Otherwise, we're not in the loop. So now, not true, okay, well, that's false. So we don't have to throw an exception. Good, we've gotten rid of most of the checks. Now you might think for our array stream, where our element data is probably an array that doesn't change, we just assign it to be final. Well, we could just go ahead and grab the length out from the very beginning, right? This sounds better. Then we don't have to look it up again, or we don't have to look at one less indirection every time we do a lookup around the loop. No, that confuses the heck out of the compiler. It's like, now this length and this element data length, I don't know that they're related unless I look all the way back here. And it's a method JIT, so it's only looking at this. And now you've confused it, and it actually has to work harder. It will still get rid of the check. But it has to work harder to do it. It has to add one extra check outside the loop to make this work, and it only works some of the time. And that's new, I think, in late Java 7. So you'd think something like pulling the size out would be better for the compiler. It can actually backfire. Okay, now we're left with a bunch of null checks. Have this element data equals null outside the loop. We have it again inside the loop. And we have action equals null inside the loop. What could we do about those? Now, you'd think the first one, that's required. What could we possibly do to optimize that? And you'd say, well, the second one, we just didn't through all this machinations of determining bounds of I and deciding whether or not it was okay. Can't we do something similar for this element data? We could assume that it's non-null from the check above. Sounds good. hard to do. And then action equals null. Well, that's required. That's the first check. What are we going to be able to do about that? And this is where things start to get fun. The first check, the one outside the loop. We absolutely cannot get rid of it. It is required. We have to do the safety check. We have to throw a null pointer exception rather than segving because that's much, much better. Well, does that mean we have to do the equivalent of checking if it's null and then having a branch and then creating an exception object? And no, none of that. What we actually do is we just say, let's say RSI, that's where we've loaded elements. Let's say length as at offset 8. Yep, we just access it. Now, what happens at a hardware level if you access a null pointer? You segfault. But this is a managed environment. We've thought of this. We have installed a segfault handler. Yeah. So, knowing that the check and branch would be expensive, we said, you know, the hardware already does this. Why are we making it work extra hard to do it? We'll just use the memory trapping operations to do it. As long as it's improbable, this isn't so bad. So you just dereference the value, your thread segfaults, you go to the signal handler, and the VM says, ah, I meant throw a null pointer exception. This is how it works. Now, trapping through hardware back into the OS and then back into user land is not terribly fast. This is not a good strategy if nulls are common. This is a good strategy if nulls are uncommon. We are counting on you being competent. Otherwise, this will backfire. But we've accounted for that too. Before I move on to the next slide, to just horrify you a little bit further, the way Stop the World works in the VM is it's a cooperative multi-threading system. All the threads have to periodically check, hey, does the GC want me to stop? The way that's actually done is by reading a memory address, and that is it. You see where this is going? You read the memory address. If the GC doesn't want you to stop, that page of memory is mapped, and you just walk right over it. If the GC wants you to stop, it unmaps the page of memory. When you get to the memory read, your thread segfaults, and excellent, you've stopped. So once every Java thread has segfaulted, we've stopped the world. Now we can do a garbage collection. But what do we do if, nulls actually happen? Well, we detect that problem. We're profiling whether or not you are a good Java programmer or whether this piece of Java code is good. We're assuming it's good from the start. We're assuming nulls don't happen. That's our speculation. And if I start showing a piece of Java code nulls, it'll give me a few chances. So I have this piece of code. I have a main. It calls a hot method, passes it the string hello. All the hot method does is call hash code. I do this 20,000 times so that it'll get just-in-time compiled. I'm turning off tiered compilation and leaving print compilation on so we have a little less noise. And then the JIT runs in a background thread, and I want to make sure the compilation is done before I start showing it nulls. So I sleep for 5 seconds. That's enough time. I could turn on blocking compilation. I didn't feel like it. Then, after the sleep, after the compile, I start looping from 0 to 10, showing it nulls. Up until now, it's never seen a null. It's assuming this isn't going to happen. So our output is this. We first get a compilation of hot method, never having seen a null. And then I show it one null, not a big deal. I show it a second null, not a big deal. Third null, and it's deciding, no. You do not know what you're doing. Apparently nulls are a regular thing for you. I'm going to make this method not entrant. It doesn't have a better one yet. It's just saying, this one doesn't work for you. What I thought was going to be true is not true. And then you go back to the interpreter. It will subsequently learn from its mistake and stop trusting you. So, as before, with tiered, we lock out a compilation, and new callers, well, they don't have anywhere to go. So they go to the interpreter. They do what's called a bail to interpreter. And the interpreter is many orders of magnitude slower than the just-in-time compiled code. You don't really want to spend a lot of time there. In the meantime, it's also learned from its mistake, and it recompiles in the background and makes another one, and then it switches to using that. If I kept running this, it would not keep making a method not entrant. It would do another compile, and then it would stay entrant. This has some interesting implications. To a large extent, the VM starts optimistic, assuming things are going to go well. And it drives slowly into a pessimistic state. So if you had a long-running server application, and some user gave you a piece of data on Tuesday that caused a null, well, that's not a problem. When they do it again on Thursday, that's not a problem either. When they do it again the next Monday, then your system may slow down, and it will come back up again, but not quite as fast as before. Eventually, the compilation may get evicted if it's not really getting used, but that doesn't happen too often. Okay, so we could actually make all these null checks better. But if we could totally eliminate them, that would be even better still. You would think we should be able to do some sort of common sub-expression or type reasoning about this element data equals null, right? It's not null outside the loop. If it was null, we threw a null pointer exception, we're not in the loop, and we're done. But this requires knowing that all the parts of that don't change. That requires knowing that null doesn't change. Okay, that's easy. That requires knowing that this doesn't change. That's sort of easy, modulo the fact that the garbage collector may move this somewhere else, but that's beside the point. This element data doesn't change. That's a bit harder. The actual easy case is the action variable. It's easy because it's a local variable. It cannot be changed by another thread or even another method on the stack. It's very easy to reason about its properties. Okay, what are you going to do? We're going to do this. It's an optimization called loop peeling. The idea is, let's not do one loop. Let's split it into multiple loops, or multiple fragments of a loop. HotSpot will actually break your loops into a pre-loop, a body loop, and a post-loop. Here we're just going to do a simple pre-loop of one iteration. So we say if I is less than 0, I is equals 0, so if 0 is less than the element data length, then we go and do the first iteration. On that iteration, well, we still have to check element data. We still have to check action is null. But after that, for the remaining 1 to however many n iterations, we've checked action. If it was null, nobody changes it. We've already thrown a null pointer exception. If it's not null, it has to be not null. It's a local variable. It stays that way. We can get rid of that check. Now this element data. Can it be changed by another thread? Absolutely. Do we care? If you're the compiler, the answer is no, don't care. You didn't tell me that it was a synchronized variable. I don't care. I'm allowed to assume it doesn't change. So then we get to say, okay, pull element data out into a local variable. After all, in hardware, you have to pull everything into a register to work with it anyway. So conceptually, you always have to work with local variables. There's no way around this. Then, that shouldn't have been element data link, sorry. You check, if element data is null, okay, that goes away, and that one goes away. Because we are now assuming we don't care if another thread changes it. This should terrify you a little bit. Now you think this is great for your array, and it is. But the compiler doesn't care whether your variable is an array or, say, a Boolean involved in some coordination protocol. If you have shared data equals something and shared done equal to true in some producer thread, you're hoping that the other thread actually sees that shared done became true from false after you've set the data. Well, shared done isn't any different than element data. It's just another variable inside the loop that we want to say doesn't change. So we can say local done is equal to shared done. Oh, if that's false, we'll just spin indefinitely. This is perfectly legal. It's the same optimization, just applied in a terrifying situation. If you want this to work, you have to make shared done volatile, and then it actually has to check every single time. It's not allowed to ever turn one load, multiple loads into a single load. This is also still wrong for other reasons in that the producer thread can be reordered as well. The volatile fixes that too. But that's for the concurrency talks. Okay, so we're good. No. Single-threaded side effects are still a problem. What? I have to maintain your single-threaded semantics. You didn't say you wanted multi-threaded semantics, so that's irrelevant. But single-threaded semantics we must maintain. Why is that a problem? It's a problem because of this except call. Could except change element data? Could it somehow have a reference to the array list or the array stream and add something to it? Absolutely it could. Terrifyingly enough, even the equals call inside of array list index of could do that. I hope we all agree that's a bad idea. But it could. And the compiler is obliged to allow you to do such things if you want to. And so it has to say, at both of these calls, element data could change. You could have added to the array list, and if you did that, well, it's not the same object anymore. Maybe I had to dynamically grow the array, and I had to create a new one and replace it, so it's not loop invariant. It changed. And if we were talking about the size, well, the size could have definitely changed. Darn. But you're like, oh, this is array stream, not array list. We said the element data is final. Yeah, yep, that sounds promising, but there's reflection. Reflection can change final variables, and the compiler is obliged to allow you to do this, even though you shouldn't. There is work going on right now to make this better, to trust final on certain types of classes, like, oh, the character array inside of a string. Yeah, we can't do that today. So our way of solving this is to just say strings are special. Everything else, eh. The other choice is we have to have a way to say, oh, you used reflection for that field. Okay, I can't do that anymore. And deoptimize and fix it. So we assume that you're not going to do something bad, but if you do, we have to correct it. That is the direction things are going. So, what are we left with? We have to prove that this call has no side effects. We have to do some form of interprocedural optimization. We have to actually look inside of action and see what it's doing. Maybe it doesn't modify our array list. I hope. And in HotSpot, the only form of interprocedural optimization is inlining. Inlining is conceptually quite simple. We copy and paste the callee, i.e. action accept, into the caller for each. That's it. You should not copy and paste your code. This is the compiler's job, and it does it quite well, I assure you. Now, the nominal explanation of why inlining is a good thing is if we have something like print the square of 9. You can imagine what square is. It's, x times x. A single multiply. And the amount of effort we'd expend putting things on the stack, doing a multiply and taking it back off the stack is disproportional to the multiply. That is true. And so we would inline it, and we'd say it's 9 times 9, and then we'd apply the simplest optimization you can possibly imagine, constant folding, and say, 9 times 9 is 81. And then we wouldn't have a call or a multiply. And that's good. I'll show you. It is good. We'll actually benchmark this. We're going to use a tool called the Java Measurement Harness. It is actually what Oracle created this to benchmark the VM. We use it as well at Azul. And it basically lets you write benchmarks as JUnit tests. And let me increase the font size. That looks big enough. Okay. So, rather than writing test methods, you write benchmark methods. And I'm going to loop over an array of element data. In this case, it's actually an int array that I set up as a final variable. And I'm going to go through that, and I'm going to pass it to some consumption method. In this case, the consumption method is easy to resolve. It is static. We know exactly which method we're calling. It's that one. It's static. And it just accumulates a sum. And with JMH, I can actually tell it, inline this method, or don't, and see what the effects of that are. And I can write multiple benchmark methods. So I could do a C-style loop, I could pull it out into a local variable, assuming that it doesn't change, or I could just use the enhanced style one. I'm going to run this benchmark. Now the way JMH actually works is it uses Maven and it uses a plugin into your compiler to create a wrapper class that takes care of all the benchmarking problems that you would otherwise have. It makes sure that that method is hot, that we're measuring the C2 phase, the server execution phase of the method, and not the interpreter phase. And it actually runs it inside of a loop. And it runs for long enough to be significant. Time measurement is not that easy. So the main thing is, you want it to reach a steady state. It'll actually print out standard deviation. And it's going to have to fill some quantum of time. So the question was, what is significant? Like on Windows, traditionally, the clock would only report 16 millisecond accuracy. So you couldn't measure something less than 16 milliseconds unless you just ran it a whole bunch of times and then averaged it out. A tool like JMH will do that for you. And it does it in a way where I'm not writing the loop myself, so I don't have to worry about the compiler accidentally exploiting other loop optimizations and completely skewing my benchmark. So you use Maven. You have to use it, create it with an archetype. It builds a target jar that's in the target directory. I'm sorry, a benchmarks jar in the target directory. And now we're running. I have instructed it to use fewer iterations than it would like to. It wants to actually do 10 warm-up iterations, 10 measurement iterations, and it wants to do that 10 times. It wants to fork the VM 10 times because the profile data may vary from one run to the next. Did I mention that the counters aren't updated atomically? They're inaccurate. Having accurate counts would be too expensive. We don't do that. Yeah. They're close enough. And for this particular case, it didn't actually matter how I wrote my loop. I could do the C-style loop. I could pull it out into a local variable, or I could use the enhanced loop. It doesn't actually matter. But if I tell it not to inline, which I did over here on another tab, the results are a bit different. Obviously, the numbers are higher. This is the overhead of the call. It's non-trivial. That is a lot of the optimization from inlining. But you'll also notice that the C-style loop actually now differs from the other two. The C-style loop differs because without the inlining in place, after the call to consume, you have to assume that element data could have changed and reload it. You can still do a lot of other optimizations just from the fact that nothing changes from the for line to the line after that where you access the element data. But after the call, you have to start over again. If you've already put it into a local variable, well, you put it into a local variable. We're allowed to assume the local variable can't change, and that's what you wanted to use. If you access heap, we have to assume that it could change. And so you end up with this deviation. So what's the performance characteristics of going to heap versus local? So I'm not too concerned that the accesses are going to be all that different. I mean, the stack will probably might be a little faster. Yeah, but it's more about the trouble the compiler can go to prove that stuff on the heap doesn't change versus what it has to do for locals. Locals, it's just, it knows. You've told it. It has a very limited scope over which it must look. And then it's all the optimizations that follow. You know, like in many cases, it won't make any difference. But in a few, it could make a dramatic difference. I'm actually looking at one right now where it's 100% difference. It's the difference in a benchmark running in 55 seconds versus 110 seconds. So it could be gigantic. So why did the enhanced for loop do well? It turns out it's not just sugar. It actually creates a local variable. It's not quite the same thing as the C-style loop accessing the member variable directly. It actually first puts the member variable into a local variable, which the compiler gets to determine doesn't change. So returning to this, just to terrify you further, if you had a call inside of your loop, if it doesn't get inlined, your code works because you have to reload after the call. If you're unlucky enough that your method does get inlined, then it doesn't work because we're allowed to assume it doesn't change. And different compilers will make different choices and can even change their mind. So, good luck finding your concurrency problems. Yeah. Okay. There is a bad joke about what the similarities are between Java and JavaScript. It's like car is to carpet. From my perspective, they're actually substantially similar. They both rely heavily on dynamic calls. This is very different than C or C++, where that's not the case. In C++, you have to mark a call as virtual if it's going to be a dynamic call. In Java, we decided that's the default. And if that's going to be your default, you better be good at it. I was reading something recently, I think it was a Forbes article, that was suggesting if you took your average Java program, C++ program, and rewrote it in Java, it would run 3 times slower. The caveat was if you took your average Java program and rewrote it in C++, it would run 3 times slower. Because the Java program is probably using a lot of dynamic calls, which the JVM turns out to be very good at, and a C++ compiler is not. Okay, so why is this hard? Well, it's hard because it's not a static call. We don't know what you're calling. How many implementations of equals are there? Are we going to inline every single one of them? No, that's not going to work. But this is a profile-guided compiler. We can do some interesting things. This turns out to be so important that the VM has 4 separate ways to get rid of dynamic calls. A backup for the backup for the backup. Yes. Yeah. So we could do it through static analysis. We could say, oh, we don't care about your left-hand side type, but we see that the new object was this. Therefore, we follow that type all the way through. We know that from the point from creation to the point to use, it's some specific type. We don't have to do a dynamic call. A C++ compiler could do that. We could also make some sort of closed world assumption. You could say that method is virtual, but looking at all the classes you ever use, there's only one implementation. That must be the one you're using. Theoretically, a C++ compiler could do that. Then, if that didn't work, we could say, well, we're going to run it a bunch of times, and we're just going to keep track of what happened. And it turns out that site only used 2 types. We can do that. And we could make sure a method is never overridden, and we could just say, that's fine. We have all of these. I'm going to talk to you about 2 of them. The closed world assumption. HotSpot calls this class hierarchy analysis, or CHA. The idea is, I have a function object, it has an apply method. Right now, you've only loaded the square class. That's it. In my closed world of what you've done so far, that's the only type of function that exists. Now, forgetting the fact that classes in Java are lazy loaded, we could always load another class that does have one of these methods, or heck, you could just make a class out of thin air. Then what would we do? Oh, and you are making classes out of thin air, I promise you. Lambdas make classes out of thin air. Reflection makes classes out of thin air. XML transforms make class out of thin air. I'm sure one of those ways you are making classes. Let's look at one case. I have my square, and I compiled this loop by running it 20,000 times and then sleeping. I can ask the VM to tell me what it inlined. I can run print compilation with a flag called unlock diagnostic VM options, which lets me use a whole bunch of other things, and print inlining. Now, print inlining by default will interleave output from multiple compiles happening at the same time. So it's also a good idea to turn off background compilation. I didn't show that in the slide. Well, you'll get some output like this. You'll see that our monomorphic apply function, which is just a wrapper around the function's apply, did in fact inline square. Now the main method, which is the loop inside of main, also inlined the apply method. It actually can see the creation and inline square. So the last one is done statically, but the first one is done based on this closed world assumption. Now when this happens, curiously enough, the compiled code does not check the type of the function. It just says, yeah, it must be a square. It's square right now, it has to be square, must always be square. How are we going to detect when something else shows up? If the compilation cannot detect the problem itself, what do you do? Well, let me show you. So this is our program with tiered compilation turned off, print compilation turned on, and a couple more things for fun. What it is doing, it is using a square. It is calling not one apply wrapper function, but 8 of them, waiting for them all to compile. And then I just sort of subtly hint that, you know, maybe there's another type of function in the world. Maybe. Don't actually need to use it. Just, yeah, there might be one. Okay, so all 8 get compiled. That makes sense. What is that? You can see the deoptimize. And before we even print out square root, which happens here, 8 methods simultaneously made not entrant. Why? Well, they can't detect their mistake. So as soon as this class is loaded, they're wrong, potentially. We don't know. So they all have to die. And they all have to die now, atomically. And the only way to kill 8 in things atomically is a stop the world pause. So those extra flags were actually telling the VM to print out the other types of stop the world pauses other than garbage collection. One of which is this type of deoptimization. And that's what this is. This is that deoptimization occurring. Yeah. It's also turning on bias locking up above. Yep. So this is a stop the world pause. It's order in based on code size of all your methods that it has to kill. And when it occurs, not only does the world stop, all the methods are locked out, new calls have to bail back to the interpreter, but all returning calls also have to bail back to the interpreter. You can imagine what effect this would have. It can be bad. Part of my work is about getting rid of these. I was very happy because in my latest release on one system, in the previous release, the last one of these happened 75 minutes into the run. Under my new release, it happened 75 seconds into the run. So that's an improvement. Far more predictable. Okay, that works if you only have one type. And it turns out it works better than you would think. This actually holds a great deal of the time. Like 50% of call sites. I don't know. After that, we go to profiling. The interpreter and C1 in tier 4 are gathering data at a call site about what types are actually used. At this call site, you use one type. At that call site, you use 2 types. At that call site, you used 3 types. It's doing this. Among tracking other things, it tracks branch probabilities so we can get rid of branches and exception tracking and the frequency of the calls and all these sorts of things. But this is the one that matters most. So after that fails, we have our stop the world pause. We're still using square quite a bit. So it adds a check that says, hey, if the function is a square, let's just use the inline code. Else, do what is called an uncommon trap. This is a bail back to the interpreter. Part of the reason is, if a second type shows up, we'd like to know it and inline it too. So after that, after we've inlined one type, we'll inline a second type using another type check, and then we'll have an else condition that's still an uncommon trap. And only after we've seen a third type will we just give up and say, use an actual dynamic call. Now you might wonder, if you're only going to inline up to 2 types, and that's as many as the VM does, why after you've done 2 types, don't you just put a dynamic call here in the else branch? Well, if we put a call there, then we have to worry about arbitrary memory effects. Then we have side effects inside of loops again. That could be bad. Whereas if we only have to worry about 2 types, we can fully analyze it, and maybe we get to keep it. So we could actually go through an example where you use 2 functions, you invalidate the closed world assumption, you recompile again, it deops again to get rid of that assumption, then you've specialized for the 1 type, it deops when it sees a second type, you add, it specializes for that, it deops again when it sees a third type, and that's it. So this 1 call could actually deoptimize 4 times. It has the stop the world one to break the closed world assumption, another one to go to 2 types, another one to go to 3 types, and if your receiver was ever actually null, we deoptimize for that too. Oh, times 3 times. So, yeah, we try really hard to make this work. So it's solved. We fixed ArrayList for each. Well, no. The problem with ArrayList for each is it takes a function object. The whole point of it is that you could pass it lots of different functions. It's guaranteed that you're going to use more than 3. At least it's highly likely. And so we're not going to be able to inline this. And we are going to have to worry about the fact that element data could change or size could change. Unless the person who wrote it says, no, compiler, you don't have to worry about that. The ArrayList for each contract actually says, the function is not allowed to change the ArrayList. The compiler cannot know that. But the person who made the contract for the API, he can. And so they've just said, you know, compiler was going to work really hard to pull all those things out into local variables so they could do all these other cool optimizations. Let's just do that so it can still do that. Even though this call is going to be megamorphic, it's going to use more than 3 types. And that's what they've done. So is the goal accomplished? No, I have not finished talking about the 5 lines of code in an hour. I could continue talking about loop unrolling, loop unswitching, vectorization, all these sorts of things. I didn't even tell you how all this interacts with the garbage collector. Heck, I didn't even tell you how we handle this .size. We use an uncommon trap. What a surprise. What you're probably starting to get a sense of is, well, optimization is an optimization problem. And I mean that in the sense of, it's like traveling salesman. It's not entirely clear whether you should go to that city next or that city next. And screwing up one of those will drastically change the outcome. It's not easy. I don't really know how to write a good compiler. Compilers are honestly just pattern matchers. We're big regexes, if we're being honest. We apply a whole bunch of heuristics that we hope only help and don't hurt. That's all we really do. If you give it things that are hard, like having to prove that this call doesn't have memory effects in a hot location, it may fail and performance will suffer. What compilers don't like is weird code. What's weird? Well, I don't know. It's whatever one of you does that you think is a good idea and the rest of you don't think is a good idea. Because how do we go about optimizing? We just run a whole bunch of programs and we see, hey, a whole bunch of programs are doing that. Maybe we should work on it. You over there by yourself doing something special? Yeah, you're over there by yourself by doing something special. You get special treatment. We don't really like big methods. In fact, there is actually a cutoff where the VM will refuse to JIT a method. It's 8,000 bytes. I have seen a system that hit this level. It is not fun. That was the hot method in the system. Don't worry, it wasn't an issue because it already had over 100 arguments, and that also won't cause it to JIT. It also doesn't actually really like native methods. Because a native method is a black box. It's a call. It can't see through. And it's going to have to give up on optimizations. If you have a crappy interpreter, Python, Ruby, absolutely go to native code. It's so much faster. But if you have a JIT and you can fully analyze all the way through, like, PyPy, then you're good. There are exceptions. System array copy, direct byte buffers, those sorts of things have special handling by the VM, but you have to know what they are. So what the compiler really likes is just normal code. Whatever that means. It will second guess you if you write abnormal code. It likes small methods. It will glue them together to find what is most valuable. I've actually seen a compilation that inlined 350 methods. You do not want to write the equivalent of a 350 methods glued together. That will, well, not JIT. It likes local variables, and it likes immutability. That doesn't mean you actually need to make your local variables final. That's not actually in the bytecode, so don't worry about it. Okay. I hope you've got a sense for how all this actually fits together. And if you want more information, well, Java 1 actually had some very good talks. And a Redditor kindly actually went and marked the minutes where each talk starts that they live streamed. So there was an introduction to JVM performance and another one on improving the performance of your applications, which show some of the same things and a lot more on profilers and everything that's wrong with them. And if you just want to keep going deeper, well, you basically have to go read the blogs of JVM developers. We're not very good about writing this stuff down. So Nitsan Wakart is my colleague, and Alexei Shipolev is the performance czar at Oracle. He actually wrote JMH. Basically, just go read anything Alexei has ever written. And if you found tiered compilation interesting, that was done by Igor Verisov, so you can go check out his stuff as well. And if you want to poke it yourself, and you don't want to remember all these arcane VM flags, there is a GUI put together by a guy in London named Chris Newland called JITWatch, which will actually show you what got compiled. It will show you a 3-panel view of source code versus bytecode versus assembly code and highlight what got inlined or didn't get inlined. He's working on showing you uncommon traps and things like that. So, all right. I hope you learned something. If you have any questions, please feel free to ask. Yeah, I mean, the good thing about OpenJDK right now is it's not that different from Oracle HotSpot. They don't, yeah, they are, that's increasingly changing because they're changing some of the thresholds and so forth to things that they think are better and not necessarily putting all those back. But the bigger thing is just they're adding tooling that they want you to pay for in the form of Java Mission Control. Fortunately, the Twitters, Netflixes of the world are contributing changes back to make it easier to follow what's going on inside the VM for profilers and those sorts of tools. So that's nice, and those are in OpenJDK. As for actually getting one to accept your optimization changes or anything like that, yeah, probably good luck. So the question was whether I could recommend a book that was any better on compilers that's not written in mathematical jargon that only a PhD in compilers could understand. Sadly, not really. And that's actually kind of why I do this talk. I think it's sort of sad that the compiler PhDs sit around in a corner talking to themselves and not to their end users who actually, use the compiler. And I think if you just understand a little bit about what the compiler does, then you can work with it rather than against it, but they just want to go talk in the corner about their crazy polyhedral loop optimizations, and that doesn't really help the end users. So no, not really. And once you get into the speculative ops, I don't know of a book that even tries to cover it. So you're pretty much stuck with the blogs of VM developers, and well, we mostly talk to each other too. So C# does take a bit of a different approach in that they don't have an interpreter. I haven't looked at what C# does a great deal. I mean, obviously they made some choices that make conservative compilation up front a little bit easier because they actually do have a virtual keyword. So dynamic dispatch isn't the default, which sort of steers people in a slightly different direction. They do have profiling capabilities, but I haven't followed a great deal on exactly what they're doing. So I can't really say.